Now, if no interval is specified for which it asks you to find the absolute min or max, which is a fair question, like in example number 3, it just says find the absolute extrema of f of x is equal to 5 minus 2x minus x squared. And you could look at this and say, okay, I know it's a degree 2, it's polynomial. That means it has to be a parabola. Parabolas always have an absolute min or max at the location of the vertex and so forth. But another principle is you can use calculus to find the vertex of a parabola just by taking a derivative. It's very, very easy. And in your homework, there should be a problem somewhere that asks you about finding the min-max value of a general quadratic equation. But anyways, it just says find the absolute extrema. So what this is probably implying is that there's only one critical value. Or, I mean, if there is more than one critical value, then one of them has to be absolute. Again, you could use a graph and everything else to help you determine this here. But if we go ahead and look at this polynomial, we could, the derivative of any quadratic will be a linear function. So f prime of x, derivative of 5 is 0. Negative 2x would just be negative 2, and negative x squared would be negative 2x. And as usual, we need to know what's the critical value, because that is the location of our hypothetical absolute min or max. And notice since it's linear, there's only one solution. So if I added 2x to both sides, I'd have 2x equal to negative 2 divided by 2. I'd have x is equal to negative 1. So there's only one critical value here. Which implies that it's the only one on the entire domain. So again, it doesn't necessarily have to be the min or max, but it probably is, just because of the nature of the question. And again, we could check the concavity. So if we look for f double prime of x, that's just going to be, well, derivative of negative 2 is 0. Derivative of negative 2x is just negative 2. This curve is always concave down because it's always negative. And it doesn't matter what x is. And if you remember parabolas, remember that parabolas could either be downward facing or upward facing. And it depends on what the coefficient is on the x squared term. This one's negative, meaning it's down facing, or concave down as we refer to it in calculus. But notice that the second derivative confirms this, that it's always negative regardless of x, as is a parabola. It's always facing down and up. It doesn't change back and forth like these other examples we've been working on in the last couple of weeks. And so again, what does this mean? Well, that means that it's a maximum value. And again, it's an absolute max in this particular case because it's the only critical value on a continuous function interval. And we can sort of summarize a lot of these ideas by creating a strategy guide for how to find absolute min and max values. But it always starts with the derivative and finding critical values, as does most of these concepts from chapter 3. C says if the interval is closed and there's more than one critical value, use principle 1. If there's exactly one, use principle 1 or 2. If it's easy to find the second derivative, principle 2 will be helpful. And the last thing is kind of the new ideas is if the interval is not closed, such as the domain is all real numbers, like the example above, or something else, and the function only has one critical value, you could use principle number 2 as well, like here, where it only had one min and max, and we went ahead and found that by just taking the second derivative and determining the concavity of the entire curve. So let's apply this to a fresh example in terms of finding the absolute mins and maxes of this rational function here, r of x. So this one's is not a polynomial because it has division. But again, we always want to start with the first derivative. And notice that, remember, if we have 28 divided by x, we could always rewrite that as 28x to the minus 1, which is helpful for finding derivatives of it. So if we're then looking at r prime of x, well, derivative of x is 1, so this would just be 4. And derivative of x to the minus 1, we drop the power, so negative 1 times 20 is 28, and we subtract 1 from the exponent. So this would leave us with 4 minus 28 divided by x squared as our function. Now, what's interesting about this is if you're wondering when could this be 0, actually this function could never be 0 because, sorry, I lied. It could be 0. Let's go ahead and set that. Let's go ahead and find that out. So if we set the, again, this is what it says to do step B, find all the critical values. I'm going to set my derivative equal to 0. Now, if I added the 28x squared to both sides, I would see that 28 over x squared would be equal to 4. I could then multiply through by x squared and divide by 4. This would leave me with x squared is equal to 28 over 4, which is, of course, equal to 7. So x would be equal to plus or minus the square root of 7. And these would be my exact critical values of the curve. And, let's go ahead and approximate because that will be helpful to know. It's about 2.6 for what intervals that will fall within. And another thing to note, this one's a little different because when it has division, you probably remember that certain functions are undefined. You're not allowed to divide by 0. It's a fundamental rule in math. So the original function r of x is not defined at 0. We say it has an undefined value that is not in the domain. And those are always going to present critical values as well for the derivative. The derivative is the same thing, right? It's undefined at 0. And so that was technically also critical value. So the critical values are going to be negative root 7, which is approximately 2.6. The second critical value would be 0 because it's undefined, a very easy thing to forget. And the third critical value would be at positive root 7, which is about 2.6 as well, but positive. And again, it's helpful to first, step B, we want to find them all. And don't forget, if it does involve division, that is important. So now, if we wanted to find absolute mins and maxes on particular intervals, if we have closed intervals, this is where we want to think about principle 1 and principle 2. So with the interval 1 to 5, there's only one critical value between 1 and 5. The other two are both less than that. So since there's only one, I would naturally think about min-max principle number 2. And to use min-max principle number 2, I need to find our double prime, the second order derivative of my function. And so if I were to take the derivative again, well, the derivative of 4 is 0, and the derivative of negative 28x to the minus 2, well, I drop the negative 2, that would give me positive 56, and then subtract 1x to the minus 3, or 56 over x cubed as the second order derivative. And that would be what I could use this to then determine the concavity. So and remember, and then I want to plug my critical value into this. That's obviously going to be positive. So if I figured out r double prime of C3, which is the only critical value on the interval, that's going to be positive, which again implies concave up, which means it's going to be an absolute min on the interval. And so this would be, and the value of that would be r of the square root of 7, because that is the exact value of the critical value on the interval 1 to 5. And that would help me find the actual value there. But I know where it occurs, and yeah. Similarly, if I was looking at the interval from negative 5 to negative 1, there's only one critical value on that, negative root 7. So same dealio. I could check, well, what is r double prime of C1, which is the only critical value to the left of 0 in here. And if I plug in a negative in here, negative cubed is still negative. Positive divided by negative is negative. So this would actually give us a negative value. Negative second derivative is concave down. And again, by minimum maximum principle number 2, this would be an absolute max on this interval. And it's going to have the value of r of negative rad 7. I can plug that in and figure that out from there. So the thing I really wanted to get to, which is a little bit different, is what about on extended intervals? What if I go from 0 to infinity or negative infinity to 0 in the same sort of way? And basically, it's the same exact idea. Use it on the entire interval. There's only one critical value to the left of 0, because at 0, it was undefined there. So it's actually the exact same answer as before, because there's still just a single critical value on the interval. and I don't actually have to do anything else. But if there were more than one, you would have to go back and think about principle number 1. Or again, if you're ever stuck or not sure what to do, you can always look at a graph to help you. So let's go ahead and type our original function in to see what the graph looks like in a standard viewing window. So we'll go zoom standard. And we actually need a much bigger Y window, I believe, in order to see what's going on here. Let's try negative 50 to 50. And what you can see is on the left-hand side on the right-hand side from 0 to infinity, there is a smallest point. There's an absolute min value, which occurs at the square root of 7, as we solved algebraically from calculus before. And there's, like, on the left-hand part, there's an absolute max here. But you can always look at the graph and say, okay, here on this interval, there's a point that's the biggest, and that can help you make this determination. But the issue is, with the calculator, it's not exact. And if you want to figure out exactly where, like if it's at the square root of 7 or something else, some other irrational number, you need to obviously solve with the calculus and use the first derivative to find the exact critical locations.